about the so-called Bayesian problem. And then I began a brief introduction to independence. Anybody have any particular questions you want to talk about? I'm doing that right now, in fact, yeah. It has to do with the size also, you know, when it gets lighter or not. Okay. Let's see, how is it? All right, it's a little lighter. Okay. Okay, anybody have any particular questions about any of the homework exercises?
Yeah, I had a question with number 6.
Which
on
one?
page 80. Number 6.
Number 6 on Bayesian?
Yeah.
Let me find it. Okay. In fictitious university, there are only great and average teachers. So in the great teachers class, 90% score C or high. Okay. So we either have great teachers or average teachers, right? So we have an average teacher or great teachers. In a great teachers class, 90% score C or higher. What did I just say, 90%? Oh, I'm sorry, that was the great teachers class, right? And so in a great teachers class, 90% or higher score C. While an average teachers class, the percentage is 80%. So it should be 10%. This should be 20%. Okay. Now, what else did I say? If 5% of the teachers are average, so probably somebody's average is 5%. That means 95% are great, just like Baruch. Okay. Determine the probability of students selected at random with a C or higher. So given a student got C or higher, determine the probability you had an average teacher. Everybody understand my tree? Any question about the tree? Okay, now it's clear that you're being given the end of the tree and you want to know about the beginning of the tree. You're given the effect of the experiment and you want to know about the cause of the experiment. So this is a classic case of the Bayesian problem. So we use a conditional formula. So I've just used a conditional formula. Now notice the numerator is where? The numerator is AT and C is right over here. So you have to get to this spot. Well, so we multiply. So that'll equal to 0.8 times 0.05. And the denominator, you either want to get here. There are two ways that can happen. Or, well, let me use the this one instead. Either here or here. So there are two alternatives. So the denominator is 0.8 times 0.05 plus 0.95 times 0.90. I'm sure you all know how to whip out a calculator and that will give you the answer. Okay, you follow that? So again, typical Bayesian problem is you're given information about the outcome of the experiment, the effect of the experiment, and you want to know about the beginning. Were there any other questions that bother anybody?
Professor, I have a question about exercise 4 and exercise 11. Page 84.
Page 84, number 11. Okay.
Page 84 is number 2 and page 85, number 11. I'm sorry.
84, number 2. Okay. So let's look at that. Okay, we have a couple of urns. Urn 1 has 7 red and 4 blue.
Why, Professor? I'm sorry. It's which exercise 4 is not exercise 2.
Okay, exercise 4. A shipment contains 10 good and 4 defective bulbs. Okay. 3 are selected without replacement. Determine the probability the first 2 are good, given the third is defective. So given the third is defective, determine the probability that the first one is good and the second one is good. You follow my notation? Technically, there should be an intersection here. The first one is good and the second one is good, given the third is defective. Okay, so we can do this with the tree. Oops, I just dropped it on my pages. Hold on. Let me just put this in my book. Okay. So we just got to do the work. So the first one could be good or defective. The problem with the first one is good is, what was it, 10 and 4? 10 out of 14. And this would then be 4 out of 14. Now you see, I don't need to do the whole tree. I'm just going to get what I need. Now, if I need the first one to be good and the second one to be good. Probably if the second one is good, will now be 9 out of 13. I mean, there are other parts of this tree. And now what can happen is a third could be good or defective. I'm putting the other stuff here. I don't really need it. And this would be 8 out of 12. And this would be 4 out of 12. So notice probability 1 is the probability the first is good and the second is good and the third is defective. Oh, I need everything else. I'm sorry. Divided by the probability that the third is defective. Now, I need to complete the, oops, sorry, where'd I go? I need to complete the rest of the tree. Okay, because the numerator I have, the numerator is just the event, oops, wrong one. The numerator is just going to be this probability right here. Okay, so let me just write down the numerator, then we'll get the other one. So the numerator is 10 out of 14 times 9 out of 13 times 4 out of 12. Now notice there's a defective here. Right, this is D2, this is D2, this is D3. Okay, so now I have to define by all the ways it can be defective. Well, let's suppose I got here. This would be this one would be 3 out of I'm sorry, 4 out of 13. 4 out of 13. And this one would be 3 out of 12, right? And this one would be, oops, this is a D3. So this one is 4 out of 14. This one is this one is 10 out of 13. This is 10 out of 13. This is 3 out of 13. And this would be 2 out of 12. And this would be 9. This would be 3 out of 12. Okay. So now notice I have to find all the cases where it's defective. So we'll do one at a time. The first one is 10 over 14 times 9 over 13 times 4 over 12 plus this one right here. And that's 10 over 14 plus, where am I going? Plus 4 out of 13 times 4 out of 13 times 3 out of 12 plus 4 out of 14, plus 4 out of 14 times 10 out of 13 times 3 out of 12 plus 4 out of 14 times 3 over 13 times 2 over 12. So notice all the different paths that the last one could be defective. So it was a little messy. You had to write the whole tree, but it was pretty straightforward to do. And what was the other one that you asked about?
The other one is question 11, Professor.
I think you should try question 11 on yourself now. If there's still a problem, I'll do it for you the next time. That's one where there's 3 different gasolines. And yeah, it's exactly the same kind of problem as the other one. So why don't you try that one yourself? And if there's still difficulty, I'll do it for you the next time.
Okay.
Okay? Did anybody else have any other questions?
Question number 9 for the same page, page 84.
Okay. A bag contains 3 coins. Okay. One of which is 2-headed, so we have a 2-headed coin. And how about it? Well, I don't like my notation. I'll call it something else. Which I call it? I'll call it the unfair coin or the one-sided coin. No, that's not good either. What should we call that? I'll just say 2-headed. Okay. We have a 2-headed coin. So there's one 2-headed coin and 2 fair coins. A coin is randomly selected, tossed twice, okay? Each time showing a head. Okay. So what can happen? Okay, so this is the fair coin and this is the unfair coin, right? So how many times are we showing that a coin is, so if I toss the unfair coin, well, let me say it a little differently. How am I going to say this? The coin is randomly selected, tossed twice, each time showing a head. So I can select the fair coin or the unfair coin, right? If I select if they're selecting a random, how many coins were there altogether? 3 coins?
Yeah,
So the
3.
probability I get a fair coin is 2 out of 3. And the probability I get an unfair coin, the 2-headed coin, is 1 out of 3. Agreed? Because there are 3 coins. They're otherwise identical. If I choose a fair coin, and now how many times are we now tossing it? Twice. I get a head or a tail, a head or a tail, a head or a tail. And what's the probability on each toss I get a head or a tail? If it's a fair coin? A half. Now, if it's the unfair coin, there's only one thing that can happen. With probability 1, I get a head. Okay, so there's my tree. So So you get a head on the first shot, given you get a head on the first shot and a head on the second shot, what's the probability that we selected the unfair coin, the two-headed coin? Okay. So now I've defined the problem, and I'm losing the pages to my book again. So in this, I have to think about getting the tree here, but that took about a minute. So now clearly you're given the outcome of the experiment. You got the two-headed coin. What's the probability? You got heads twice. What's the probability it was the unfair coin? Well, this is P of F1 intersection H1 intersection H2 divided by the probability. You got a head on the first and a head on the second. Okay. Well, the probability is the unfair coin, you got a head, is right here. So that's going to be just 1/3 times 1 times 1. The denominator, though, can happen. You can get a two-headed coin. You can get a you can be here, right? That's how you got two heads, and you can be here. So what does that give me? So that gives me 1/3 times 1 times 1 plus 1/3. I'm sorry, 2/3, right? The other one. Let's start again. I get 1/3 times 1 times 1 plus the only other way I can get two heads is 2/3 times a half times a half. And that gives me my answer. Let's do some arithmetic. This looks like it's pretty simple to do that. 1/3, 1/3, 1/3, 2, 1/125. Check my arithmetic. I did that quickly. Okay. So it was a little bit more complicated. The tree was a little bit more involved, but we got our answer. Okay. If other things are bothering you, we'll do them the next time. So now let's talk about independence. Independent. Now, we know from the conditional formula or simply from the multiplication principle, which is we cross multiply, that P of A and B equals to P of A given B times P of B. So notice in general, and I write this because it's so important, and some of you made the mistake on the first exam, P of A intersection B is not equal to P of A times P of B. It's not equal. In fact, we see it's equal to a conditional probability times P of B. Now, if in fact B and A are independent events, this will be one definition. If A and B are independent, what do we mean? It means one doesn't affect the other. Then P of A given B is just P of A. If they're independent, it means one outcome doesn't affect the other. So A is not affected in any way by B. Or equivalently, P of A intersection B is equal to P of A times P of B. So we have the following definition. A and B are said to be independent events if and only if P of A intersection B equals P of A times P of B, or equivalently, P of A given B equals P of A. Now, we generalize this definition, and I'll make some observations in a moment as well. It is, suppose I have three events, A, B, and C. A and B and C are independent events. Every one is independent of every other. If P of A intersection B intersection C is equal to the product of A times B times C, and P of A and B equals P of A times P of B, P of A and C equals P of A times P of C, P of B and C equals P of B times P of C. All possible probabilities of intersections are equal to that product. And in general, A1, A2, up through A sub n are independent if let's say it differently, if the probability of any combination of intersections is equal to the product of the probabilities. Okay. So there are two kinds of problems that can arise. One problem is to prove events are independent. So here are the two typical problems. Problem number one, use independence to compute probabilities. And number two, prove events are independent. Meaning we have to prove that the product of the intersection is equal to the product of the intersection is equal to the product of the individual probabilities. Those are the two typical problems that can arise. And before I go any further, let me make an observation. If A and B are independent, what can you say about A and B prime? Or A prime and B, or A prime and B prime? Oops. Yes. Problem is, how would you prove it? Example, suppose I want to prove, here, I'll do one, I'll let you do the others. Given A and B are independent, prove A and which one do I want to do? B prime. I'll do this one as an example. Okay, so what do we know? We know that P of A intersection B, because since these are independent, this is equal to P of A times P of B. So that's a given, because they're independent. Now also observe that I could write A as A intersection B. What I'm really having in my head is a Venn diagram. Union A intersection B complement. Again, if this is A and this is B, here's A intersection B complement, right? And this, I'm sorry, and here is A intersection B. Put them together, you get A. And these are mutually exclusive events. Therefore, the probability of A is equal to the probability of A intersection B plus the probability of A intersection B complement. Now, by independence, this term right here is equal to P of A times P of B. So if I bring it over to the left, I got P of A minus P of A times P of B equals P of A intersection B complement. If I factor out a P of A from here, I'm left with 1 minus P of B. But 1 minus P of B is just P of B complement. So this is P of A times P of B complement equals P of A intersection B complement. So I've just proven that these two events are independent because the probability of their intersection is equal to the product of their individual probabilities. So there's a typical proof of how one can prove two events are independent. If you wanted to prove A prime and B prime, what I do is I'd rewrite this as A union B complement and take it from there. I'll let you do that one. So let me walk through a couple of examples, illustrate some facts. Okay. And how we use this. So there are two kinds of problems. Again, one problem is assume independence and use that to solve a problem. And the other problem is to prove their independence. So the first example I do is the following. I draw example number one. I draw two cards from a deck with replacement. Okay. That means I draw one card, put it back in the deck, mix the deck again. Okay. Determine the probability, both are aces. Okay, so let A be the event, A1 be the first card is an ace. And ace of 2 would be the second card is an ace. Okay. What's the probability that the first card is an ace?
4 out of 52.
4 out of 52. Okay, now I put the card back in the deck, right? What's the probability that the second card is an ace? Also 4 out of 52. Nothing's changed. So observe, the question is, what's the probability that the first is an ace and the second is an ace? Well, it should be clear from this problem that each card drawn is an independent event, right? The drawing of the first card didn't affect the second because I put the card back into the deck. So since they're independent, so I'm assuming the fact that this is independent, this is just equal to the product of the individual probabilities, which is about each of these, by the way, is 1 out of 13. So I get 1 out of 13 times 1 out of 13, or 1 out of 169. Now that's sort of a silly example, but it helps. It illustrates that I've used independence. I'm going to walk through a couple more examples with you. Okay. Let's suppose, I have two people, A and B. Did I give them names? Arthur and B are working on a problem. Working separately on a problem. Oops. The probability Arthur solves the problem. I'm just making up numbers now, not looking at the book. 60%. Whereas the probability B solves the problem will make B smarter is 70%. Determine the probability the problem is solved. So I'm going to let A be the event. Arthur solves the problem. And B will be the event that B does. Okay. So what am I asking you to find? What am I asking you to find? Anyone? I'll tell you what. I'll give you 2 minutes. See if you can figure it out. Fair enough? You got 2 minutes. Well, how are we doing? Anybody?
Professor, do you mind scrolling up?
I'm sorry?
I couldn't
didn't
see the
hear you.
full. I couldn't see the full question.
I have two people working separately on a problem. The probability that Arthur solves a problem is 60%, and the probability that B solves a problem is 70%. Determine the probability the problem is solved. So what am I asking you to find? No. Why?
It's A union B.
Yes, in order for the problem to be solved, at least one of them must solve it. So the problem is to find P of A union B. Because if at least one of them solves it, it's possible they both could solve it. But if the problem is solved, at least one of them solves it. And that will equal to P of A plus P of B. This is one way of doing it. minus P of A intersection B. Well, we know P of A is, what was it, 60%? P of B is 70%. Now, did I give you what P of A intersection B is? I did not, but if they're working separately, then it's assumed that they're working independently, correct? So A and B are independent events. So this would just equal to P of A times P of B, which is 0.6 times 0.7. What does this give me? 1.3, right? 13 minus 0.42. And when you're done, you get the answer. You whip out your calculator or you do a longhand. So there is a fairly simple example. The hard part here was to write down what the problem was. Okay, let's talk about a couple of other ideas here. Won't find it. Where did I put my stuff? Okay. Now, students often mix up the notion of independence with mutually exclusive, okay? So consider the following. Remember, A and B are disjoint or mutually exclusive if their intersection is the empty set. Okay, meaning they have nothing in common. Suppose in my sample space, I toss a coin twice. If I toss a coin twice, I get two heads, a head and a tail and a head, and a tail. So that would be the sample space. And suppose I define A to be getting two heads, and B will be the event of getting two tails. Okay, and notice P of A, well, hold on, let me go. So observe, firstly, A intersection B is the empty set, right? What does that mean? That means, of course, that the probability is equal to 0. On the other hand, P of A is 1/4. P of B is 1/4. So P of A times P of B is 1/16, which clearly is not equal to their intersection. So clearly, these events, A and B, are not independent. Just a simple example to show that. Now let's look at another event. Now, suppose I define two more events. C is the event head-head or head-tail. And notice, by the way, P of C would be 2 out of 4, right? Or 1/2. Same sample space. And suppose D is the event head-head, tail-head. Notice C intersection D is just 2 heads. I should have said this P of D, by the way, is also 1/2. But P of C and D is 1/4. So notice C and D is not equal to the empty set because they have something in common, namely two heads. But notice the probability of C and D, which is a quarter, is equal to P of C times P of D, because each of these is a half. So these events C and D are in fact independent. Okay, so notice the importance, the difference between, mutually exclusive or disjoint and independence. It's possible to have any kind of combination of them. Now, let's look at the following question. And suppose I toss a pair of dice, okay? And I define two events. Where are my events? I prepared these in advance. A, their sum is 8, the sum of the spots. B, the first die, think of there being separate die, one is red and one is blue. I'll call one the first die. The first die, well, the first is a 3, is the number 3. So question, are these independent events? Intuitively, and then let's prove it. Okay, so can we reason intuitively? Would these be independent events? Why? It could be dependent on B. In fact, let's see that. Because if we let's look at A. If we write out what A is. If the sum is an 8, I get a 2 and a 6, a 3 and a 5, a 4 and a 4, a 5 and a 3, a 6 and a 2. Notice what I just underlined here. It's possible that the B influences the A because there could be a 3 there. B would be 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. So the probability of an A, by the way, is 1, 2, 3, 4, is 5 out of 36, right? The probability of B is 1, 2, 3, is 6 out of 36. Notice A intersection B is just one event, 3, 5. And this probability is 1 out of 36. Now that's not equal to P of A times P of B, which is 5 out of 36 times 6 out of 36. So clearly A and B are not independent because the first die affects the second die. Another observation, so I'm just walking through examples where it was intuitively obvious, or at least it could be intuitively obvious, that in this problem, A and B clearly can't be independent, but I also wanted to show you how one can prove it. One other remark about probability is things sound different that are the same. That is, consider the following problem. Suppose I have a family of 2 children. Well, then the sample space could be first is the male and the second is a male, or the first is a male and the second is a female, or the second is the first is a female and the second is a male, and female, female. By the way, notice I can change this problem. Instead of saying I'm talking about children, I can say I'm tossing a coin twice. One of them is think of male as being heads and female as being tails, so the other way around. Notice it's the exact same problem. So let A be the event. The first child is male, and B be the event. The second is female. So notice A is male, 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 female. B is male, female, female, female. Okay, notice P of A is 2 out of 4. P of B is also 2 out of 4. Notice A intersection B is what? Male, female. The probability, therefore, is 1 out of 4. So observe that P of A and B is equal to P of A times P of B. That tells me A and B are independent. So having kids is like tossing coins. What happens on the first one birth does not affect another birth. So every time you have a kid, the way, if everything is equal, is the probability is always a half. They're independent events. Okay. So how am I doing time-wise here? I need okay. So independence is a pretty straightforward event, a pretty straightforward idea. And again, as I said earlier, when I started this topic, there are 2 kinds of questions. One question is, prove they're independent. And the second question is, if they are independent, use that to solve the problem. Now, it turns out the sample spaces don't have to be finite. We can have an infinite sample space. I'll illustrate that in an example in a moment. But before I do that, I need a preliminary. I need to remind you about a geometric sum, which you learned about in algebra. So let me just remind you. Suppose S is S sub n is the sum of 1 plus R squared up until R to the n minus 1. I have a sum of n terms. And in a moment, I'm going to ask what happens when n goes to infinity. But I just want to show you how I can compute this sum. If I multiply both sides by R, what happens is I get the 1 becomes an R, the R becomes an R squared, and the last one becomes R to the n. So notice if I subtract the second line from the first line, only 2 terms survive. This term and this term survive. All the other terms cancel, so I'm left with 1 minus R sub n. If I factor S sub n out, we can simplify this expression, and we get S sub n is equal to 1 minus R to the n over 1 minus R. Okay, so that's the first observation. I want to make sure I'm not forgetting anything. Okay. Now, suppose the following. Suppose R is a number smaller than 1 in absolute value. So now the question is, let's define S to be the limit as n goes to infinity of 1 minus r to the n over 1 minus r. What do I get? If n goes to infinity, what is r to the n going to go to? If n is a number, if r is a number between minus 1 and 1, smaller than 1 in absolute value, what happens to it as n goes to infinity?
R gets smaller,
And smaller, so what's its limit?
0.
0. So this becomes just 1 over 1 minus r. And that's called the sum of a geometric series. So for example, if I had 1 plus a half plus a quarter plus an eighth and so on forever, what is r in this problem? How do I go from one term to the next term? What am I multiplying by?
1/2.
1/2. So the sum is 1 over 1 minus a half, which turns out to be 2. Suppose I have, let's see, and so on. Notice, by the way, now it doesn't start with 1, it starts with 2/3 squared. So if I wanted to do this, I'll give you a short way in a second. So notice if I factor out 2/3 squared, what's left? 1 plus 2/3 plus 2/3 squared, and so on, right? Now, in this part right here, what's r going to be? It's 2/3, right? From one term to the next is 2/3. So it's 1 over 1 minus r, or if you like, 2/3 squared over 1 minus 2/3 is 1/3. And of course, I can simplify this. This becomes what? 4 over 4/3. Okay. By the way, notice it's always the sum of the geometric surge is always the first term in the series over 1 minus what I call r. Okay. Because you can always factor out the first term, so you get 1 over 1 minus r. Okay, so why did I do this? Because it turns out there are a whole class of problems. In fact, you'll see a little later on when we talk about geometric distributions. This will come in handy, but let me state a problem and we'll figure out how to solve it. And you'll see why I even talked about this. So where's my problem? Okay. So I'm doing example number 4 now. Mark and Ann play a game. And here's the rule of the game. They each toss a pair of dice. Mark must toss a sum of 9, and must toss a sum of 4 and goes first. Okay, so who wins, meaning who gets, who tosses their sum first? Who does Ann get? Does Ann get the sum of 4 before Mark gets the sum of 9, or the other way around? So my question is, what's the probability that Ann tosses a 4 and tosses 4 before Mark tosses 9? Okay, so let's make sure we understand the game. Ann and Mark are each going to toss a pair of dice. Ann's objective is to get a sum of 4. Mark's objective is to get a sum of 9. Ann goes first. What's the probability that she wins? Okay. So let's let A sub I be Ann wins on the ith toss. And similarly, M sub I will be Mark wins on the ith toss. So what can happen? Ann could win on the first toss, right? That's one thing that can happen. But if she doesn't, then, so here's one way Ann, the probability that Ann wins is she wins on the first toss. If she doesn't win on the first toss, when else can she win? What else could happen? She could lose on the first toss. Mark can lose on the second toss. Oops, Mark. And Ann can win on the third toss. Or Ann can lose on the first toss. Mark can lose on the second toss. Ann can lose on the third toss. Mark can lose on the fourth toss. And Ann can win on the fifth toss. And this can go on infinitum. It can go on forever. So the probability that Ann wins is the sum of all these probabilities because they're all mutually exclusive. Only one of these can happen. Be P of A1 plus P of A1 comp intersection M2 comp intersection A3, or P of A1 comp intersection M2 comp intersection A3 comp intersection M4 comp intersection A5, and so on. So notice Ann has to win on an odd toss. Now, every time you toss a pair of dice, they're independent events. Your previous toss doesn't affect any of these. So we can start writing these out. So P of A1, what's the probability that Ann wins, by the way? What is P of A sub I? Well, in order to win, she has to get a what? A 4, that's a 1-3, a 2-2, and a 3-1, right? That's 3 out of 36. And the probability that Mark wins on any toss, he has to get a 9. How do you get a 9? You get a 3-6, a 3-6, a 4-5, a 5-4, and a 6-3, which is 6 out of 36. Let me make sure I got my numbers right here. up to 1/12, and the other one is 1/9. Something's wrong here. The probability that Mark contains a 9 is 4 what did I say? A 9 is 3, 6, 4, 5, 5, 4 is 4 out of 36. I'm sorry. So we have P of A sub I is 3 out of 36, which is 1/12. And P of M sub I is 1/9, 4 out of 36. So the probability that Ann wins is equal to, well, P of A1 is just 1/12. Now look at this term, okay, right here. That's equal to the product of their probabilities. So P of A complement, what is P of A? Is 11 out of 12 times 8 out of 9 times 1/12 plus, now I'm doing this one up here. It would be, I lost my place. 11 out of 12. 8 out of 9, 11 out of 12, 8 out of 9, 1/12, and so on. So let's see what I have. If I factor out a 1/12, I'm left with 1 plus 11 times 8 over 12 times 9, I'll simplify it in a second, plus 11 out of 12, 8 times 9, and the other ones are the same thing twice, and so on. So this turns out to be 1/12 times 1 plus, let me simplify this right here. 4 goes 2, 4 goes 3. What's that? 22 over, well, let me check my arithmetic later. 22 over 27. And so on. So this is equal to the first term, A over 1 minus R. R is 22 over 27. So what does this give me? This gives me 1/12 times 27 over 5. 3 goes 9. 3 goes 4. 9 over 20, is that what I got on the text? I don't remember that number. Let me just see. Yeah, we're good. Okay. So the probability that Ann wins turned out to be 9 out of 20. So by complementation, the probability that Mark wins, you can do it directly, or by complementation, it's 11 out of 20. So the purpose of this example is to show you, I'm sorry. Well, what does 9 and 11 add up to? It's okay. I just want to make sure you understand complementation. Okay. So here's an example of effectively where I could have said this problem a little differently. I could have rephrased this problem as how could I have said it? I could have said, no, it doesn't pay to say it. I just want to rephrase it in the way as a geometric distribution. But basically, notice what's happening here is the only way Ann could win is if she wins on an odd toss, because she's going first. Okay, so I've illustrated independence. In this last problem, of course, we're using the fact that when you toss a pair of dice, each time you toss a die or the dice, we have independent events. Okay, this looks like a pretty good place to stop. How's my time here? 11:56. Okay. So please make sure you do the exercises in section 2.5. What I do next is we introduce a new word. We're going to introduce a word called random variable, which is really a misnomer. Because a random variable is just a fancy way of saying the word function. So we all know from pre-calculus or algebra what a function is. And what a function does is it assigns a number by some rule. It gives you a rule where you relate one number to another. You're often used to functions as using letters like f of x or g of y or things of that nature. We'll use slightly different symbols here, and I'll talk about that the next time. Let me just stop the recording. Okay.
Recording stopped.
And let me get out of this window.